So we're going to introduce a term called a convex function in operations research kind of language, which in calculus class you would have called a concave up function. And then I said before, we won't think of sets as concave, but we will think of functions as concave. And a concave function is what you would have called a concave down function in calculus class. I actually like the whole concave up, concave down system better than convex and concave. That seems less arbitrary to me, and it kind of gives you a hint as to which way things are going. But if you're reading stuff in operations research and optimization, you'll see convex and concave functions, so you need to know that too. So the big question is, why should we care whether a function is concave up or concave down? Well, minimizing concave up functions is easier than minimizing concave down functions, or things that are neither concave up nor concave down. Why is that? I'll let you think about it, and then we'll talk about it later. One thing I can tell you that's not a spoiler is that if functions are concave up or convex, then there are special methods that run faster to optimize on those functions. You can read whole books and get computer code about convex programming, which is like linear programming or nonlinear programming, but for the special case of the objective function being convex and minimizing. So how should we define a function being convex or not? Well, think back to how it was defined in calculus class. Try to remember what that was. Well, in calculus class, you probably said if the second derivative is always positive, then we'll call the function concave up. So some examples are x squared, obviously. Also, e to the x, which goes like this from my point of view, and e to the negative x, which goes like this from my point of view, which is a little weird, and maybe it took you some time, like it does for many people, to think about e to the negative x is always decreasing, but we call it concave up, even though it never actually goes up as you move from left to right. So that takes a little bit of getting used to. But its second derivative is always positive. And then concave down would be that the second derivative is always negative. Again, this is from calculus class point of view. So obviously, negative frowny parabola, log x, is, again, interesting. Log x is always increasing, but its second derivative is always negative, so it's concave down increasing. And then 1 minus e to the minus x is a classic horizontal asymptote sort of situation. It starts at the origin and does that as we move off to infinity. Again, I'm not sure if you're seeing this mirror imaged or not, but go ahead and imagine 1 minus e to the negative x. So those are some important functions that are concave up and concave down. And let's think about definitions some more. What about absolute value? That looks like a v. Would you call that concave up? And you might say, oh, absolute value is just something that mathematicians use to torture people. It's not used in real life, but it is actually used in applied math in lasso regression, for example. The A stands for absolute. Or the function max of 0, x, which is a flat line along the x-axis until you get to the origin, and then a 45-degree line. It's also called a rectified linear unit, or ReLU, in neural networks. Would you call that concave up? Would you call that concave down? Got to think about it. Well, one way to think about it is if you filled a function shape like y equals x squared with an infinite amount of water from above, then that filled set would be a convex shape, right? If you filled x squared, you would get a convex shape up here. The same thing for e to the x. Some people would say, well, the water would all run off this way, or e to the negative x. But again, we're using an infinite amount of water, so it's just the region above that function. And that would still work for absolute value. If you filled that with water, you would get a convex shape. And if you filled this shape with water from above, you would get a convex shape. So can you think of another way of defining a concave up function or convex function that doesn't involve an infinite amount of water? Because I don't happen to carry around an infinite amount of water usually. So think about how you might define that. Well, the way we defined convex is that if you pick 2 points, then everything between those points stays within the region. And here, everything within the region is everything above the function, because we're filling it with water. So you could say a function is convex if every secant line segment, so pick 2 points on the function, draw the line segment between them, if that stays on or above the function, then we'll say, for every pair of points on the function, then we'll say the function is concave up or convex, because it gives us a convex region above it. So let's take a quick look at this formula. Alpha x1 plus 1 minus alpha x0, that's what we said is a point on the line segment between these 2 points. And then we're evaluating the function there. So that's the function value at a point that's interpolated between the 2 points. And then here, we're taking a y value and another y value, and then we're interpolating between those. So that'll be a point on the line segment between them. And so if for every alpha between 0 and 1, this point on the line segment is above this function value at an interpolated x value, then we'll say that the objective function is concave up or convex. And in the next video, we'll go illustrate that kind of thing and talk more about convexity.